Morning, everybody. Can you hear me?
Yes, I can hear you. I can hear you.
Let's wait a minute. We have 83 people on. Let's see. I'll wait for 100. All right. So let's begin. We are going to continue our series on training deep neural networks. So here's what we've seen so far. That neural networks are universal approximators. They can model any function, but in order to model any specific function, we have to train them to do so. And we train them to minimize a total error on a training set, which quantifies the error between the function you want to model and the function that is currently computed by the network. And we do this through empirical risk minimization. The ERM itself minimizes a loss function, which is a function of the network parameters. And so we use variance of gradient descent to perform this minimization. Gradients are computed using backpropagation. So we also saw that vanilla gradient descent may be too slow or unstable. So we can get better convergence through second order methods that normalize variation across dimensions and using adaptive or decaying learning rates that can help you escape from local minima and improve convergence to a better minima. And we also saw that methods like RMSProp that decouple the dimensions can make convergence better because you're able to control the learning rates better. We also briefly mentioned momentum methods, which emphasize directions of steady improvement and de-emphasize unstable directions. We didn't spend a lot of time on that. We will go over that in more detail today. So moving on, here are the topics for today. We're going to look at incremental updates, and we'll revisit trend algorithms. We'll look at generalization and other tricks of the trade in the next lecture. So let's start with the first topic, incremental updates. So when we train a network, here's the problem as we pose it. You're given a bunch of training points, and at each of these training points, you're given the value of the function that you want to compute. Then, well, once you set up your network, your initial value of the network parameters gives you some function. And over the entire training set, this function is going to be wrong pretty much at every training point. So we aggregate gradients over the entire training set. And when we aggregate gradients over the entire training set, these gradients tell us exactly which way to move the function at each of the training points to better approximate the function that we want to estimate or model. So they would tell us, for example, that if this blue line is the function we want to model, and the red dotted curve is the function currently modeled by the network, our gradients will tell us that the function must be pushed up at these 2 points. It must be pushed down at these 2 points and then pushed up at this point. So we adjust the value of the function at all the training points to make because we are aggregating gradients from all of these training points in order to make the outputs closer to the required value. And then that will give us a new function value because all the parameters have been updated. And then once again, the gradients will tell us which way to adjust the parameters so that the functions, the error reduces at each of the training points, and that gives us a new value for the function, and so on. So we keep repeating this till we get arbitrarily close to the target function at the training points. The key over here is that we are adjusting the value of the function at all training points to make the outputs closer to the required value. Because the gradient, the loss, is a function of all the training points, and the gradient, because we want to minimize the error everywhere. And so the overall gradients gets contributions from every single training point. So this is your conventional gradient descent. We try to simultaneously adjust the function at all the training points. So this means we must process all the training points before we make a single adjustment. This is what is called a batch update. So can anybody tell me what the problem might be? This is what we intend to do. This is what we would like to do. But what could the problem be with this approach? Anybody? Any problems with this approach? All errors get summed to zero? No, there are errors. If the errors get summed to zero, there are no errors, computation cost. So can you tell me why is it computationally expensive? Anyone? Maybe you can do so by answering this first poll. So we'll use the first poll. Right? Can you see the poll? So 15 seconds. All right, let me stop this poll. Here's what you guys thought. And stop sharing. Okay. Which of these statements are correct? Anybody? The actual loss function that we must minimize requires batch updates, true or false? Yes or no? Anybody want to reply? True or false, guys? Really? True or false? Okay. What is the objective we actually want to minimize, guys? What is the function you actually want to minimize? Anybody? Do you want to minimize the expected divergence over the entire space, right? And so our loss, which is the average divergence over the entire training set, is an approximation to the expected divergence over the entire input space. So that is the best we can do. The function that our loss is the average divergence over the entire training set. So if you want to minimize it, you want to perform batch update. That making sense? That is the only thing we need to do because we are trying to minimize the function everywhere. Does that make sense? Yes, no? Okay. So second one, batch updates minimize the total loss over the entire training data, true or false? So they optimize the actual loss function, true or false? Third one. Right. And so why would you call this false? Batch updates, Rishabh. So why would that be false? The optimize, what is the actual loss function? It is the average divergence over the entire training set, correct? And batch updates are correcting over the entire training set. So this is in fact the correct thing that you would be minimizing, right? Right, and so the statement, fourth statement, batch updates require processing the entire training data before we perform a single update. True. So all of these statements are true, right? So what we really want to do is this. This is the only true objective we've got. Everything else that you would do is going to be some kind of an approximation, right? So the problem here is that for this to work, you want to minimize the error at every single training point, correct? Which means that you have to process the entire training data to make sure that the error at every single training point is minimized. But that is too slow. You'd have to process the entire training set before each update. So here's an alternative. The alternative is, let's make incremental updates. Now, to give you an idea of how this works, imagine I have a lump of clay and you want to shape it into a doll. So the ideal thing you would do is to have some kind of a, you sprout like 5,000 arms and simultaneously press it all over the place until the whole thing sort of shapes into a single doll. But then if you've ever worked with modeling putty, you know that this is not how you do it. You don't have 1,000 arms, you don't have 5,000 fingers. And so you can't really, mold your putty all at once into the shape of your doll. So what do you do when you have putty and you want to make it a doll? Anybody who's worked with putty, everybody has played with putty in your childhood, right? What do you do in this case? Anyone? How do we do it? You want to make this doll from the putty. How do we do it? You press one area at a time, right? You poke this, and then this goes down. And then you poke this, and you gently prod and poke each point one at a time. And the problem here is that if you poke it out here, it's going to pop up out here. So how do you control for that? When you're poking and prodding one spot at a time, how do you control for it? You make each of those corrections small so that things don't, doing something at one point, you don't try to push one spot all the way to the position of the doll. It will cause other things to pop. You do it slowly, one spot at a time, right? And so this is exactly the same process we're going to use. We're going to adjust the function one training point at a time, but we're going to keep the adjustment small. So you pick up maybe this point, push the function up here. When you push it up here, it's going to go up everywhere a little bit, but not change so much far away from this point. Then you pick up some other point, correct the function up there. Then you pick up a third point. Here at this point, the function is overshot. You push it down a bit. Then, each of these corrections makes an adjustment to the function. And so eventually, when you've gone through all the training points or processed all the training points, you would have adjusted the entire function at all of the training points. And this can potentially give us an greater overall adjustment than if we had made a single batch update. This making sense? Over here? Yeah, right. So this is literally like modeling putty. You poke it one place at a time, but when you poke it, you don't poke it till it goes all the way to the, to the target, because then it's going to keep popping up all over the place. You make gentle prods at each point until you shape your putty. So that's exactly what we do with this function. Now, this is the incremental update. As you go through the training data, you go through each of the parameters, and after each training instance, what happened? After each training instance, you make a correction to the function parameters after each training instance. And eventually, when you've gone through all of the training instances, you would have made a correction to the entire function, at least at all the training points. And in fact, when you do this, your iterations can make multiple passes over the data. A single pass over the entire training data is called an epoch. So an epoch over a training set with t samples means that because you're making an adjustment after each sample, you will make t updates of the parameters. And so within our pseudocode, you would be passing over the entire data multiple times. Each pass over the entire data is called an epoch. Within each epoch, after each data instance, you're going to correct your parameters. That's one update. So if you have T training instances, you'd make T updates within each epoch, and you can have multiple epochs as you update your parameters. So this is making sense so far? Everything. Yes or no, right? Okay. Now, can you think of any caveats over here? What can make this break? Anybody? What could make this break? No. This is a single instance. Where's the batch size coming in out here? You're throwing terminology at me. Where is the batch? Right? So what could, what are the caveats? Anybody? Take a guess. We may run into a loop. We can cycle, right? So here's what. Let's say these are my training samples. And I have 4 training samples out to the left, 4 to the right. The dotted line is my target function. And this is my current function. So then when I begin making corrections, I go process the first 4 samples, the ones to the left. What will happen? If I process these 4 samples, what will it do to this function? Anyone? If I just process these 4 samples first, it's going to push the left side down, right? Boom. It's going to push the left side down. But when you push the left side down, this can make the right side pop up. So then I process these 4. And this is going to make the right side go down, but then this can cause the left side to pop up. So then if I go back to the left, it will make the left go down and the right pop up, and it will keep bouncing back and forth. And you can get a seesaw result. So what can you suggest a solution to this? Can you suggest a solution to this? Anyone? Go through the points randomly, right? So what we can do is we must go through the points randomly to get more convergent behavior. You maybe make a correction over here, randomly select this point, push it down here. Then you randomly select something and maybe you get something on the right side. You push that up here. And so you have to randomize the order in which you sample the points to prevent such cyclic behavior. Otherwise, it will not work. So the pseudocode, how do you randomize it? Within each, if you keep going through the data points in the same order, you can get cyclic behavior. So between epochs, you're going to have to permute your data instances to change the order. And only then is this process going to work in any reasonable manner. That making sense so far? Yes, no? Okay, so far so good. At least half a dozen people are saying yes. So here's the story so far. In any gradient descent optimization problem, presenting training instances incrementally can be more effective than presenting them all at once, provided the training instances are presented in random order. And so this approach is called stochastic gradient descent. Why stochastic? Stochastic is because we are presenting the training instances in random order, one at a time. So this approach holds for any function optimization, and so also for training neural networks. Now, why does the process of incremental updates work, and under what conditions? For the why, first I'm going to consider a very simplistic explanation that's often given, and it will give you some sort of an intuition. Let's look at an extreme example. Now, when you perform gradient descent, the actual loss function is the average divergence over all the training points. So the derivative of the loss with respect to any network parameter is simply the average of the derivatives of the divergence with respect to the parameters for each training instance. So the overall gradient is the average of the gradients of the error for each of the training instances. Now, if you pick any given training instances, maybe for one training instance, the gradient points this way, for another it points this way, for the third it points this way, for the fourth it points this way. So the overall gradient that you choose is the average of all of these gradients, which is perhaps given by this red line. And that is the direction in which you would move the network parameters. This is what happens, right? In your standard training. So now consider, but this averaging works nicely if all of your training data are diverse. Now, if I have many training instances which are all identical, in this case, what would happen if I took the average divergence over all of the training samples? What would happen? Anyone? If all my training points were identical, what does the average look like? Anybody? Maybe the question's not clear, right? It's just going to be the same. Every single training instance will have the same divergence. So the average is going to have just the divergence as same as the divergence you'd get for one training instance. And so what would happen is that although you processed your entire training data, the net correction you got was exactly the same as if you'd seen only one training point, because the average was the same as the divergence for any individual training point. Whereas if you perform stochastic gradient descent, every training point is going to see an updated parameter. And so you're going to get over T training instances, you'll actually end up getting T corrections. And so even though the individual corrections may be smaller, this cumulative correction could be much greater than this case. That makes sense to everybody?
Yes, Prof. Just if I'm getting you well. So are you saying we should randomize every epoch or
Yes, every epoch. Otherwise, otherwise it's cycling, right? It will use cycle.
All right. Got it.
Correct.
Yeah.
And so now, instead of all of the data points being exactly the same, suppose they were very close to each other, would you still expect to see greater benefit from stochastic gradient descent than from a single batch update in this case? Yes, because the gradients are going to be very similar to each other, right? So when will the one begin to lose out over the other? Anybody? When will the one begin to lose out over the other? Take a guess. When they are very, very different. As the data become increasingly diverse, the benefits of incremental updates decrease. They don't entirely vanish, we'll see more of it, but you have to be more careful. So this is a high-level intuition, okay? Let's go into a little more detail. What are the considerations and how well does it work? For this, instead of a neural network, I'm going to start off with a very trivial problem to explain one simple concept. Now here I have a bunch of training data points and I want to find somewhat of a principal component, which like a regression line through the origin. I want it to go through the origin and I wanted to model the data. So basically what I'm trying to do is to find the line, find this hyperplane such that the projection, the average projection error for all of my training data points is minimized. Simple problem, right? So if I were performing batch processing, I would find the line through the origin that has the lowest overall squared projection with respect to the data. But instead of batch processing, let's say I began performing stochastic gradient descent. Then first I got this training point. Then my line is going to go this way through that training point, zero error, right? Then my next sample is this one. My line is going to swing around and go through this training point, zero error. Then I can pick up my next point. My line is going to swing around and go through that point. And then my next point is going to go through that point. Will this ever converge? If I'm always chasing the latest training data instance, will this ever converge? So what is the solution? A solution, anybody? Weak model? Any other ideas? Have more than one point? Any other ideas? Decrease the updates, right? So you update the model to always minimize the error on the training instance, but you shrink the learning rate with iterations. So with increasing iterations, it will swing less and less towards the new point. So your first update may go all the way to this guy. The next one, instead of swinging all the way to this data point, it's only going to go part of the way there. Then the next one, instead of swinging all the way here, it's only going to go part of the way here. Then instead of swinging all the way here, it's going to go even less. All the two, it's going to make even less of a swing to that point, and so on. And eventually, as with increasing iterations, if you keep decreasing your learning rate, eventually it will arrive at the correct solution, where adding new data points is not going to swing it too much, because the learning rate is so small that it's not going to really change your solution. Did this make sense to all of you guys? Okay, and so update the model to always minimize the error on the latest instance, but then we must shrink the learning rate with iterations for convergence. So correction for the individual instances with the eventual minuscule learning rates will not modify the function. If I go back to my pseudocode, I have two things. Again, I still have to randomly permute my training data in each epoch, but then this learning rate is going to keep decreasing with each update. After each update, the learning rate must change and it must become smaller. Now, how much must it become smaller? Is there any constraint on how fast the learning rate must reduce? So let's look at that, right? Consider this, even if let's say I'm going to try write scribble. Say for any parameter, let's say my derivative d loss over dw, the magnitude, is always lesser than or equal to some constant c. So this is my upper bound on my derivative, right? So if I have a learning rate of eta, then what is the largest amount by which I can correct my parameters in an update? If eta is my learning rate and the derivative is bounded, and it always is, because you never have infinitely steep loss functions. Those are horrible things. So we try hard not to permit them, right? So then in this case, what is the maximum by which this maximum value for this correction? Anybody? What will it be? It's going to be eta c, right? You know that this correction, delta w, is less than or equal to eta c. Is this making sense to everybody? Yes or no? Okay, so now this eta is the learning rate, this one. Okay. Now, suppose my learning rate changes with iterations. So the kth iteration, the learning rate is eta k. Then what is the maximum value of the corrections over infinite iterations, infinite updates? That is going to be the total correction, delta w, is going to be less than or equal to summation over k, eta k. Oh, what happened? Eta k c. Is this making sense to everybody? This one? This is my c. Yes or no? Is this making sense, guys? Okay. So in other words, okay, within any update, the maximum values correction is eta k, right? If eta changes with iterations, the total correction is upper bounded by summation over k, eta k c. That makes sense, Aditya? And so the delta w total correction is lesser than or equal to c times summation k eta k. So now for your model to actually find the optimum, this upper bound must be large enough for you to span the entire gap. So let's say your optimal point is out here. This is your optimum. And your initial estimate is out here. You want this distance, this gap from here to here, should be less than the upper bound on the number of corrections you want to make. So if this gap is, say, g, You want to make sure that G is less than or equal to C times summation K eta K, right? Because if it's greater than that, then you'll never get to the optimal point. That making sense? Is this making sense? Okay. How far can your initial point be in the worst case? How far can your initial point be in the worst case? Your initial point can be, in the worst case, it can be infinitely far away, right? So what does this tell you about this guy? What must this value be? If G can be infinite, C is a finite value, so this summation must be infinite, correct? Yes or no? Right. At the same time, you want the etas to decrease with iterations. And so we have these two constraints on the correction terms, the learning rate. The sum of the learning rates must be infinite. It must not be otherwise the entire parameter space cannot be searched. At the same time, the squared sum must be finite because you want the learning rate to keep decreasing. Otherwise, you'll keep oscillating. These two conditions must be satisfied. What is the fastest converging series that satisfies both requirements? What is the fastest converging series which is squared summable but not absolutely summable? Anybody? Anyone? You've done this in college. Anyone? Squared summable because you wanted to shrink with time, right? That's this guy, 1 over k. What is the sum of 1 over k? This is infinite. At the same time, 1 over k squared is finite. So this is the fastest converging series that satisfies both of our requirements. More generally, the learning rates are heuristically determined. And typically, we are going to have learning rates of this kind where we have some initial learning rate for a long time. Then we have some other learning rate for a long time. And then we have some other learning rate for a long time. But then whatever schedule you use, you will eventually find that this schedule has the property that both of these conditions are satisfied. If it doesn't satisfy both conditions, then you're not guaranteed that you will actually be able to learn the function. This makes sense to everybody so far. Everybody good? Okay. And so what does SGD work like? Here's an example from a very trivial problem. This is actually from k-means clustering. And the square is because you want it to shrink. And so the math for it just says that how do you make sure that it keeps going down and eventually go to 0? That's where the square comes from. I'm not going through the math for that, but it has to shrink. It has to converge. The point is it has to converge. Okay. So here's an example from k-means. K-means, you get different initializations. So in this example, they tried to perform k-means clustering. I got this off the web. They tried to perform k-means clustering on a bunch of training data. And this is how the total error converged with iterations. And this little bar shows the variation across runs. This is when they perform batch update. This is when they perform stochastic gradient descent. What do we find? SGD converges much faster than k-means. But at the same time, there are two obvious problems that stick out. What are the two problems? What can you see? The two obvious problems. Anybody? It is, what are the two obvious problems over here? This is the variance across runs. The final solution is crappy, number one. Second, the variance across runs is very large, right? Yes or no? Okay. And that leads us to our second poll. And let's see, poll 2. Can you see the poll? 15 seconds, guys. Okay, let me stop this. Here's what we thought. Okay. Stop sharing here. Go back. Okay, first statement, true or false? It's true. Online methods are better where you make computations as data come in. Second one, true or false? True. Third one, fourth. Right? So SGD is an online version of batch updates. It can have oscillatory behavior. If you don't randomize the order of inputs, it can converge faster than batch updates, but arrive at poorer minima. And convergence to the global minimum can only be guaranteed if step sizes shrink across iterations, but sum to infinity in the limit. So let's try to understand why you see why you see this kind of behavior, why we have this wild variance, and why that can result in poor estimates, right? Look at this. This converges much faster. It just converges to a poorer minimum, right, Delphine? So let's see why this happens. Now let's go back and look at what is the objective function you really want to minimize. Again, guys, what is the objective function we really want to minimize? Anybody? What is it? The expected divergence, right? You want to take, the error is the integral of the divergence over the entire input space, which is the expected divergence. This is what you want to minimize. The problem is you don't have the function everywhere. We can't compute the expected divergence everywhere. So we get the divergence at a bunch of training points. Our loss is the average divergence over all of the training points. And we are hoping that by minimizing this, we are actually minimizing the expected divergence. Now, why can we hope so? So first, I'm going to give you some math. Here's the thing. First, if I take x1 plus, suppose I have two random variables, x1 plus x2 plus x3, right? And I take the expected value of all of these and divide by 1/3, say. What is the expected value? What is the expectation of this? x1, x2, and x3 are random variables. Then what is the expectation over here? Does anybody remember? What is it? Linearity of expectations, right? It's going to be x1 bar over 3 plus x2 bar over 3. By bar, I mean the expected value, right? Plus x3 bar over 3, and so on. So in general, if all of these are identically distributed, then it's just going to be 3 times x bar over 3, which is, cancel this out. This is just x bar. Is this making sense to everybody so far? Okay, so what this means is that if I take the statistical expectation of the guy on the right, that is going to be exactly as the statistical expectation of the guy on the left, which means that in expectation, which means if I take lots and lots of different training sets and compute the average divergence over all of these training sets, and then if I compute the average of these averages, that is actually going to be the true divergence function, that the true objective we want to minimize, which is this term. So because the expected value of the empirical risk is exactly the same as the expected divergence, this is what is called an unbiased estimator. This is why we believe that if I minimize this guy, I'm also going to be minimizing this guy. Okay? It doesn't matter how many training points you have. The expectation on the right is the same as the expectation on the left. So minimizing this guy, you can kind of hope that you're minimizing the actual objective function. Now, let me give you another thing, a couple of other things. Suppose I have a training a random variable x with a variance v, right? What is the variance of x over n? If y equals x over n, what is the variance of y? If the variance of x is v. Anybody? What is the variance of y? Come on, this is easy. If the variance of x is, this is going to be v over n squared, right? Now, suppose I take random variables x1, x2, x3 to xn, right? And each of them has a variance exactly equal to v. What is the variance of the sum of these independent random variables? Anybody? What is the sum of these? That's going to be n times v, right? So what if it's x1 over n plus x2 over n all the way to xn over n? What is the variance of this guy? What is the variance of this one? It's going to be n times, but each of them is locally v over n squared. So this n squared and n will cancel. This is v over n, right? So if I take a look at this term over here, the variance of this term is simply the variance of the divergence function of x divided by n. That's the variance of this term. That makes sense to everybody? Can I get like a couple of dozen 25 thumbs ups, please? Because this is kind of key for the rest of the explanation. That makes sense to you guys. Okay. Out of 250 people in class, less than 20 are actually responding, guys. Please do. Because I'm depending on your feedback, right? Okay. So now, let's go back. What this means is that for this one, the variance of the empirical risk is 1 over n times the variance of the divergence. The variance is proportional to 1 over n. The larger the variance, the greater the likelihood that the estimate of the W estimate that you get will differ significantly across different training runs. If the variance is small across training runs, you'll get a smaller estimate. Okay. Now, if I go at stochastic gradient descent, in the case of stochastic gradient descent, I'm not taking the average of many divergences. It's just the divergence over a single training point. Even so, the expected loss is the same as the expectation of the divergence. So even for the STD case, the sample divergence is an unbiased estimate of the expected error, okay? Expected divergence. But the problem is, n in this case is 1. You have only one training point. So the variance of the sample divergence is the variance of the divergence itself. This is n times the variance of the empirical average minimized by the batch update. So this is what the math says. Did this make sense to you guys? I don't expect it makes sense, but did it make sense to you guys? I'll try to explain it with pictures. This makes sense to you? Okay. Honestly, when I read this, it never made sense to me. So I had to draw pictures and convince myself. So I will try to do so for you. Here it is. This blue line is the function you want to minimize, correct? The red line is the function that you have currently estimated by the network. And you have a bunch of training points. So when you try to minimize the error across the batch error, you're trying to minimize the error across all of the training points, which will tell you that you have to push the function up in these two places. You have to push the function down in these three places and up again in this place. That is the advice you'd get from these 6 training points. But suppose I had a different set of 6 training points. These guys could end up over here. And in this case, the advice I'm getting from the same number of training points, it's just a different set, is that the function must go up everywhere. And so if you just believe these training points, you would also be pushing up the function in these places where it is the wrong thing to be doing. Suppose I had a different set of training points. Suppose I had these as my training points. In this case, the majority of my training points are telling me to push down the function. And so I'd end up pushing the function down everywhere, right? So depending on the set of training points I choose, the advice that I get from my training points, my training data can be wildly different. That's what we mean by variance. That different training data instances, training sets can give you completely different recommendations. That makes sense? Yes or no? Right. So can I get a few more thumbs up? Okay. So how would you fix this? One simple solution. Higher is better? Do you really want it to be? So this one, uh, is this good? That in one case, it asked me to push up the function. In another case, it asked me to push down the function. Same function, right? Is higher a better thing or a worse thing? What do you guys think? Is it better to get completely different recommendations from different training sets, or do you want them to be consistent? Do you want, right? You want, if the different training sets give you completely different recommendations, that is not good. You want it to be consistent. What is a simple solution to making it consistent? Anyone? More samples. Just having more samples means that, as the data set increases, the chance that you're going to get completely different recommendations from different data sets is going to go down. This is what we mean by saying the variance of your loss goes down as you increase the size of your training set, and therefore the variance of your estimate also goes down. But then when you're performing SGD, you have only one training instance. So if your training instance fell here, you're going to say, oh, I'm fine, my estimate is perfect. If it fell here, you're going to say, I have to push my function up. If I fell here, it fell here, you're going to here push my function down everywhere. And so you can see how with SGD, because you have just one training instance, the choice of training instance can completely change the advice that you get from it, which is why you're going to get wild variations in the loss function across different runs, which is why you get such wild variation. And that loss function is what you're minimizing, right? And so which is why you get such large variances in your estimate itself, and which is why your loss itself is so much poorer, even though it converges. Whereas for the batch updates, because the number of training instances is much larger, the variance is much smaller, and it converges much more cleanly. This makes sense to everybody? Yes, no? Okay, so here's the thing. Batch updates are good, low variance, better estimate, but they're very slow. SGD, it converges very fast, many updates per epoch, pathetic variance, crappy estimates. So can you give me a solution? How can I combine the two? Anyone? How do I combine the two? So SGD uses the gradient from only one sample at a time and is consistently high variance, but also produces significantly quicker updates than batch. So there's a good medium. Adjust the function not at just one point, but a randomly chosen subset of points, keeping the adjustment small. If the subsets cover the training data, you'd have adjusted the entire function. As before, vary the subsets randomly in different passes through the training data. So maybe in one update, you get these 3 samples, you make your corrections. Then the next time around, you pick a different set of 3 samples, you make your corrections and keep go and so on. So in your pseudocode now, you actually choose batches of instances. You compute the average gradient over the batch, and that's what you use for correction, right? So, and so now the mini batch loss is the average divergence over a small set of training samples. And as it turns out, this is also the expectation of this is also the same as the expected divergence. So this is also a unbiased estimator, because the expected value of the mini batch loss is the same as the actual objective you're trying to minimize. But then the variance is 1 over b times the variance of the divergence itself. Now, if you look at this, So if I were to plot this, right, the variance of the loss, and this is my mini batch size B, and this is N, just sorry, guys. I'm here. My neighbor's drilling his wall. And I just, okay. So here's where we have, this is your variance, right? So this for B equals 1, the variance of your loss function is the variance of the divergence itself. And as you keep increasing the batch size, this is 1 over n times this variance of the divergence, right? And as you keep increasing the batch size, you will find that this curve falls very quickly, like so. And so there's a sweet spot somewhere around here where your batch size is large enough that you're not very far from this variance, and yet small enough that you can get the advantages of incremental updates. That makes sense to everybody? Right. And so this is what we will do, right? The mini batches, if you look at how mini batch updates work in this example, you find that mini batch updates, they have only slightly greater variance than batch updates. They converge as fast as stochastic gradient, and the error they achieve is comparable to what you would get with batch updates. So mini batch performs. So where did I lose you? Mini batches. So here, the point is, you agree that if I work with mini batches, the variance is going to be smaller, right? And because the variance is proportional to 1 over B. And 1 over B is going to go down like so. The largest batch size, of course, is your training data size. And so it begins up, the variance of your mini batch loss begins approaching the variance of your batch loss very quickly as you increase the batch size. And so you get more stable updates. So that's what we find over here. When you use mini batches, you actually get much better convergence, and it's much faster. So this makes sense, the whole thing so far? Okay. Anya, what do you mean that makes the data noisy? Can you explain? It doesn't change the data, right? You're just using subset of the data. The variance is still going to be greater than the batch update case, but it's going to be much less than the stochastic gradient case. It is similar to SGD. It's very similar to SGD, except that, again, in the SGD case, the variance is just the variance of your loss is in each step is simply going to be the variance of the divergence. Whereas in the mini batch case, this is going to be the variance of the divergence over B. This 1 over B term is what increases the stability of the loss across iterations. Okay. So convergence is now, how do you define convergence? Is generally defined in terms of overall training loss, not sample or batch loss. And it's infeasible to actually measure the overall training loss over the entire training data after each iteration. So more typically, we estimate it as the loss on your latest batch or on a held out set. So all of the losses and all of the convergences that you're reporting in your experiments, for instance, they're somewhat bogus. The only thing that you're guaranteed is the convergence over the entire training set. It doesn't mean that the loss is going to necessarily converge on the latest batch. The fact that it does is a good thing, but just because it has not converged on the latest batch doesn't mean that it has not converged on the entire training set. and vice versa. So in practice, training is performed using mini batches. The mini batches size is generally set to the largest that your hardware will support without compromising overall compute time. Larger mini batches is less variance. Larger mini batches also means fewer updates per epoch. Delphine, you always, regardless of whether you're performing mini batch or SGD, you have to randomize the data in each epoch. Otherwise, it doesn't work, right? You have the same cyclic behavior. And convergence in both cases depends on learning rate, which must decrease with the update iterations. So it must be absolutely not summable, but must be square summable. So a simple technique is to fix the learning rate till the error plateaus, then reduce it by some fixed factor and so on. And you can also have adaptive updates, where the learning rate itself is determined as part of the estimation. We will see that shortly. But first, let me give you a poll. Okay, 10 seconds. All right, let me stop this here. Here's what all of you thought. And let me get back. Okay. Mini batch descent is an online version of batch updates. True or false? True or false? It's true. Online is, you keep updating as the data comes in. So you could use it in streaming mode, for instance. It's faster than SGD when the batch size is 1. True or false? False, because mini batch is the same as SGD when batch size is 1. The variance decreases with batch size. True or false? True, right? It approaches batch updates in variance, but approaches SGD in efficiency with vector processing in large batches. True or false? Also true, right? Beautiful. You guys get it. And so the story so far, in the case of SGD, you're presenting training instances one at a time. This can be more effective than full batch training, provided they are presented in random order. For SGD to converge, the learning rate must shrink sufficiently rapidly with iterations. Otherwise, the learning will continuously chase the latest samples. SGD estimates can have higher variance than batch estimates, but mini batch updates operate on batches of instances at a time. Estimates have lower variance than SGD, and so convergence rate is theoretically worse than SGD, but because you perform, you can actually use the vector processing and such like, you end up with much better convergence. To answer your question, yes, once you increase the batch size, you can increase the learning rate. So far, so good. Any questions so far? Any questions? I guess not. How do you choose? Okay, so you want to choose the largest mini batch size that you can stuff into your memory, basically. Because the larger the mini batch size, the lower the variance of your loss, and the lower the variance of the estimate, the updates. That answer your question? So batch update will have variance too, unless you have infinite if you have infinite training data, then the variance is 0. Otherwise, the batch update is going to have a variance which is proportional to 1 over the size of your training set. That usually tends to be very small. That's all. Because your training set is typically very, very large. That answer your question, Mansoor? Yeah, okay. Right. So now we're going to go back to trend algorithms. In the last class, we briefly mentioned this. The mini batch size should be a portion of the actual data set. If you could fit the entire training data set into RAM, you should. That has the lowest variance. provided your training data are diverse, which they usually will be. So now let's go on to trend algorithms, right? So we saw, for example, in the last class that when you have a loss function, the optimal learning rate in one direction is going to be different from the optimal learning rate in the other direction. So you can, instead of, if you start off from some point, instead of going smoothly to your objective, you can end up doing something like this, swinging up and down, right? Spending a lot of time. So how did we say we could deal with this? Anybody remember? It's if I want, instead of doing this, if I'm doing this, how could I deal with this? So what we do is we observe that at each point, you have a horizontal component to the gradient and a vertical component to the gradient. Again, here you'll have a horizontal component to the gradient, but now the vertical component to the gradient is this way. Over here, the horizontal component of the gradient is this way. Over here, the horizontal component of the gradient is this way, but the vertical component is downwards. Here, the horizontal is this way, but the vertical is this way, right? So what are we seeing at each point in this example? If I have updates like this, then over here, the horizontal is forward. The vertical component of the gradient is asking me to go down, right? Here, the horizontal component of the gradient is asking me to go forward, but the vertical component is asking me to go up. Here, the horizontal component of the gradient is asking me to go forward, but the vertical component is asking me to go down, which is why when I follow the recommendations, I keep swinging, right? Over here, what is the gradient telling me if this is my update at this point? What is the horizontal component of the gradient telling me, forward or backward at this point? Forward. And the vertical? Up, right? So what do we see? When you have behavior of this kind, it's converging cleanly in this direction, but it's swinging in this direction. And that is immediately apparent from the gradients, right? And so suppose I took a running average of the gradients. Then in this direction, the gradients are always consistent. So the running average is always going to be a significant value pointing forward. But in the vertical direction, this downward and this upward and this downward and this upward, they will cancel out. And so in the vertical direction, I'm going to end up with very small net gradients in the vertical direction, right? And so we said if you use a running average of all of the gradients, then you expect to damp out nasty oscillations while enhancing the consistent directions. Everybody remember that? Yes, no? Right. Give me a yes, no. I'd like to see a dozen yeses. Or at least did that make sense to you guys? Okay. It turns out that when you're doing stochastic gradient descent, this kind of behavior is going to be even more dramatic because even if you're doing mini batches, each time you're looking at a different loss. You're looking at a different set of data. And so because of that, you're going to get a lot more of this crazy oscillation. And so the necessity to damp out these oscillations becomes greater. And so what we do, the momentum method uses the running average of all of the gradients. You have G1, G2, right? And so on. At each time, you're going to take 1 over n, summation I equals 1 to n, Gi. And this running average of gradients is what you will use for your correction. Now, the problem is this running average of gradient, it's hard to, you don't want to keep track of all of these gradients, but then you can do it very simply. You can say delta W at the kth step is going to be some alpha times delta W at k minus 1th step, plus some beta minus, because you're going against the gradient, minus some beta times the gradient, the kth gradient. So this is your running average formula. Where does it come from? Just look at it this way. If Wk is the average gradient after k steps, then WK plus 1, I mean delta WK, right? Then delta WK plus 1 equals K times delta WK minus the latest gradient divided by K plus 1, right? Is this formula making sense to you guys? Is this one making sense? What does this look like? It's basically K over K plus 1 times delta WK minus 1 over K plus 1, the latest gradient, right? Or more generally, some alpha times delta WK minus 1 minus beta times the latest gradient. So that is how you keep a running average of all of the gradients, and that is what you use in your correction. So the correction to the parameter is going to be some beta times the previous correction minus some eta times the gradient of the loss in the current in the current patch. And that loss, of course, has been computed using the previous estimate in the network, right? And this correction is what you use to correct your network parameters. Is this making sense? Over here? Everybody? And so typical beta values are 0.9. This is your learning rate, right? And this running average will get longer in directions where the gradient retains the sign and becomes shorter in directions where the sign keeps flipping. So here's what the momentum method is going to look like. Suppose you start from here. Say the previous correction was this way. Then you're going to compute the gradient over here, which is in this direction. So the correction recommended by the gradient is going to be this guy. So that is this term. But to this term, you're going to add some scaled variant of the previous gradient. And this is the net correction that you're going to be using to update your parameters. That makes sense? Yes, no? Over here? Okay. So that's your momentum method, momentum update, right? Now, observe that the momentum update steps are actually computed in 2 steps. First, you take a step against the gradient. Then you add a scaled version of the previous step. And that is going to give you the net correction. It turns out that if you reverse this order, it ends up being more optimal. What we will do is, instead of first taking a gradient step and then adding a scaled version of the previous step, we will first take a scaled version of the previous step and then make a gradient correction from here to get the net correction. So is the change of is the change of the sequence of operations making sense to you over here? Yes or no? It turns out this is the famous Nesterov's update rule. And it turns out that this is much more optimal than simple. This guy here is called the momentum method. It's called momentum because the current correction, it's almost as if you're maintaining a momentum from previous corrections. And yeah, momentum can reduce the randomness of SGD. And Nesterov's update rule is an improvement on that because you continue with the momentum and then make the gradient, take the gradient step. So here is the Nesterov's method. From the previous step, you take a step which is beta times the previous step, and then you add some eta times the gradient computed at the new point, which is WK minus 1 plus beta. So this is the new correction, and that is what you correct your parameters with. So Mehul, why does the order matter? Here's a nice pictorial illustration, but the math of it is there in a very nice paper, right? So again, this guy, you're adding the correction because over here you have minus eta. So the going against the gradient is already factored in over here, okay? So, but here's a very nice pictorial illustration. So this was from Hinton. Suppose this was your previous step, and this is your optimum. If you were following the momentum method, you'd first go here and then add a scaled version of the previous step and end up here. Whereas if you were following Nesterov's, you would first continue here and then take a step against the gradient, which would end up here, which is much closer. And so you can actually, for nice convex functions of this kind, you can show that this Nesterov's method is considerably more faster to converge than simple momentum. This makes sense to everybody so far? Yeah, okay. Now, where does back propagation figure? If you're using the momentum method, this gradient is computed using backprop. And this loss over here is the instance or mini batch loss. If you're using Nesterov's method, this gradient is computed using backprop. And this loss is the SGD or mini batch loss. That's all. Okay. So now here's what we got. Here is your standard update rule, right? Now this update rule, we found that this gradient can be very noisy, particularly if you're using SGD or mini batch. And so we smoothed this out by using running averages. Do you see a second term over here that can also be corrected? Do you see something else over here that can also be corrected? Anyone? This guy, right? So how does that figure? Look at this. So this momentum methods fix this term to reduce unstable oscillation. What about this term? Now look at this. I have three different updates, okay? In this case, you have vertical swings of this kind. Here too, you have vertical swings. Here too, you have vertical swings. In all three cases, the running average is the same or very similar because the positive and the negatives cancel each other out. But should I be using the same learning rate in all three cases? Should I trust these oscillations as much as I trust these oscillations? Or should I trust these guys less? What do you think? How many of you think I should trust this more? How many think I should trust this less? Just let me know. Right? Okay. How do I know that I should trust this less? Simply, I have moved a lot more. I have moved a lot more, right? It's not the average motion. It is the net motion, right? So if I take the average motion in both cases, the average is going to be small. But instead of taking summation gradient, if I took summation gradient squared square root, this guy, the root mean squared value is going to be much larger for this one than this one. Yes? This is going to be small for both cases because the positive and negative oscillations will cancel out. Here, it's going to aggregate, right? And so this is what we will do. That makes sense? Yes, no? Guys, I need you guys to be prompt, otherwise I run out of time, okay? So this is what we will do in RMSProp. We are going to maintain a running average of the squared derivative in each direction. And we'd come, which is basically, we want the mean squared derivative, the RMS value, or the, we want the mean squared, not yet taken the root. For that, we will maintain a running average of the squared derivative. So just like we maintain the running average of the derivative, this is exactly the same, except it's a running average of the squared derivative. And then the learning rate itself is scaled by the inverse of the root mean squared value of the derivative. This plus epsilon is to prevent division by 0. And so you can see how this will naturally sort of dampen oscillations where you have wild oscillations and give you learning rates where the oscillation is not so swinging, not so wildly. Right? And you can also see that if you have a constant slope of this kind, then when you have a constant slope, this is simply going to be the partial derivative, because in every case, at every step, the derivative is going to be the same. So this and this will cancel out, and all you're left with is the sign of the derivative. Now that, which was the learning method where we only considered the sign of the derivative? Anybody remember? Did this make sense? Did this make sense? That if you have a constant slope, at every point the slope is the same, right? So the RMS value is simply going to be the slope itself, so it will cancel out. All you're left with is the sign, right? So it turns out that's why this was called RMSProp. RMSProp is basically viewed as an extension of RProp. You know, because the magnitude of the derivative is being cancelled out. Now, so RMSProp, momentum methods correct this guy. RMSProp corrects this guy. It only adapts the learning rate. Momentum only smooths the gradient. What is the obvious next step? Anyone? What is the obvious next step? Combine them, right? So how do you combine them? Beautiful. Let's combine both. This is Adam. Adam is simply RMSProp with momentum. You maintain a running average of the mean. You also maintain a running average of the you maintain a running average of the derivative. You also maintaining a running average of the squared derivative. And then you use the same. Let's skip this for the moment. If you focus on this guy, this is the same as your standard gradient descent rule, except here you're using the running average of the derivative and you are normalizing by the inverse of the RMS value of the derivative. So Adam is simply RMSProp plus momentum. This making sense to all of you guys? Yes or no? Okay. Now, what is this crazy bit over here? Why do you need this? This is just a hack. It turns out that typically you initialize this guy as 0. Typically, you also initialize delta as something close to 1. What will happen? Initially, this is 0. Because if delta is close to 0, this also becomes 0. So this never gets updated. These things don't get updated simply because of the manner in which we initialize these things and the values we choose for these parameters. So this 1 minus delta raised to k deals with it. What it does is it ensures that the delta and gamma terms do not dominate in the early iterations. And at higher iterations, as k becomes large, because both delta and gamma are less than 1, these will basically disappear and you end up with the simple vanilla update rules. Okay, so this is basically a hack. But Adam in general is just RMSProp plus momentum. That makes sense to everybody? Yes, no? Okay. I have some typical values. Typically mu0 is set to 0, delta is set close to 1. 1 minus delta will become 0. So without this denominator, mu k will stay close to 0 for a long time. The denominator ensures that updates actually happen. For large k, the denominator just becomes 1. That's the basic idea. And they have many more variants of the same theme, add a grad, add a delta, add a max. The nice thing about these things is that now you don't have to adjust your learning rates in theory because the update rules automatically adjust your learning rates, supposedly. And this also takes care of variations in your derivative. So typical values for RMSProp, you'll be eta is 0.001, gamma is 0.9. Adam is going to use the same thing with this delta of 0.9 as well. Delta is the learning rate for the mean, gamma is the learning rate, is the update rate for the mean, gamma is the update rate for the squared derivative. Anyway, these are just engineering details. It turns out that in spite of these, you still need learning rate schedules and such like. I'm going to go over by about 30 seconds. So I'm going to actually give you this poll. Can you see the poll? Make it quick. Only 30 seconds. All right, 10 seconds, guys. stop this. Here's what you guys thought. So anybody want to tell me? Vanilla SGD considers the long-term trends of gradients, does it? Yes or no? First one, no, right? Momentum considers the long-term average, true or false? RMSProp only considers the second order moment, but not their average trend, true or false? True. Adam considers both, average trend and second moment, true or false? Right? Trend-based optimizers like Momentum, RMSProp, and Adam are important to smooth out the variance of SGD or mini batch updates, true or false? True. Right? All of these are true. Very nice. So this guy, he actually showed, he compared the different optimization methods for different loss functions, different functions. I don't have time to go over it, but these behaviors, you can actually look at these things and see, get a very nice feel for how these things behave. And you can see that SGD, for example, simply gets stuck in a saddle point, whereas all of the other methods manage to escape from it. And in particular, you always find that Nesterov's accelerated gradient and momentum, regardless of the function, they tend to approach the optimum pretty quickly. Here's another one, right? SGD gets stuck. The rest of them go down. So the story so far, gradient descent can be sped up by incremental updates. Convergence is guaranteed under most conditions, but the learning rate must shrink with time. Stochastic gradient descent, you update after each observation, can be faster than batch learning. Mini batch updates, you update after batches, can be more efficient than SGD. Convergence can be improved using smoothed updates, particularly trend methods and things like RMSProp and Adam, right? So that's the end of today's lecture. I'll wait for questions, but before that, guys, if this lecture made sense, can you give me a thumbs up? I'd like to see there are 200 of you on the class. I'd like to see maybe 100 of those, so I know I'm going the right way. Good. Thank you. That helps, right? That really helps. And I will stop the recording.